So, hi, welcome. Our purpose for today is to give an alternate form for the slope of the tangent line. Come in, sit as far forward as you can. Yes?
Are we getting our grades today?
Your test. I have your test graded. I can get you back at this time, and I will do that at the end of class. Yep. I want to first of all go over one problem from the homework, the one involving fraction, because very often people will have some confusion about how to deal with fractions, and there's no need to be confused, but sometimes people are. First of all, a quick question. If I want to subtract two fractions, then I need a common denominator. And how do I find that common denominator? Multiply what? Yes, I multiply factors. That's exactly right. So here my factors are 2 and 3, and there it is. If I had something more sophisticated, I would definitely not want to use 12 times 18 as my common denominator, although I could. I want to use the least common multiple, which is going to be, let's see, this is 2 squared times 3, and this is 2 times 3 squared. So I would want to use 2 squared and 3 squared, which is 36, as my common denominator. All of you very familiar with that procedure, right? Well, let's keep that in mind as we consider now the derivative, the slope of the tangent line for the function f of x equals 1 over x, and I believe it's at the point x equals 4. Am I correct about that? You guys did the homework.
Oh, homework.
Yeah.
Yeah.
Is that the correct value?
Yes. Wait. No, it's at a equals 2.
And 2. You could also specify at x equals 2, and that would be fine as well. And so I'm going to set it up, first of all, by saying dy dx equals the limit as h goes to 0 of f of x plus h minus f of x, and all of that over h. This is the form, and as I mentioned before, at this stage of the game, you should be writing the form every single time, just like this. I've seen some people try to jump in and substitute. You're not in that much of a hurry. Slow down and write the form every single time, because we're going to have a second form starting today, and if you are not in the habit of writing those two forms, you will get them confused. Every year, I get students who try to mix and match pieces out of the different forms, and it's their own darn fault for not writing the forms. So if you do not have the forms written on your work, I'm going to just put redo and give it right back to you. Is everybody really clear? Okay, we'll see if we're clear. All right, now we can substitute. Our function is 1 over x, and our value of x is 2. So that my direct substitution now gives me exactly this. This is, in some sense, the hardest part.
Yeah.
All right. Now the question is, what do I do with my compound fraction? And the answer is I'm going to clear the fractions or combine the fractions. I can either clear or combine. Most of the work that I've seen has involved combining the fractions, so let me do that at this time, and then I'm going to come back and show you how clearing the fractions is actually preferable. To combine the fractions, I need a common denominator, so let's identify. What are the factors in my two fractions here? 2 plus h is a factor,
And 2.
and 2 is a factor. Therefore, my common denominator is going to be 2 times 2 plus h. So I can write that common denominator. Now, I need to get my denominators like that, so I'm going to multiply each fraction by 1. Please notice, I am not multiplying by 2, which would be 2 over 1. I am multiplying by 1, written in the form 2 over 2. And the effect of multiplying by 1, which is 2 over 2, is to leave 1 over 2 plus h with the same value. It's still 1 over 2 plus h, but it's going to be in the form 2 over 2 times 2 plus h. See, same value when I cancel. And likewise, I'm going to multiply top and bottom here by 2 plus h, which is again multiplying by 1, so that the value does not change. And then the h down here stays where it is. Now something lovely happens. I get 2 minus h, or 2 minus quantity 2 plus h. And like so, and these cancel. And now at this point, in order to deal with the compound fraction, I'm going to remember that division is multiplying by the reciprocal. So our form for that is a divided by b is the same as a times the reciprocal of b. And so I can write that in this way. This is the limit as h goes to 0 of the numerator here times 1 over h, just like that. And now it's really clear what happens. These cancel, giving me -1, and I can now let h go to 0 so that I get -1 over 4. Questions on that? Now, I want to show you my favorite way of dealing with this, which is to clear rather than combine fractions. Because, it's my favorite way because it immediately gets rid of the compound fraction. See how we had to carry these compound fractions down like this? Rather than do that, what I'd like to do is to take this limit as h goes to 0 of 1 over 2 plus h minus 1 over 2 all over h. And I am going to multiply the entire fraction by 1 again. But specifically, I'm going to multiply the entire fraction by that common denominator, just like this. Keeping in mind that I'm multiplying the top and the bottom, just like that. And now watch what happens. It's really lovely. In the first term, I get 2 times 2 plus h divided by 2 plus h, and that leaves me with 2. And in the second term, I get 2 times 2 plus h divided by 2, and that leaves me with 2 plus h. And in the denominator, I get h times 2 times 2 plus h. And lo and behold, in one move, I have gone from a compound fraction to a single fraction, a simple fraction. And this is a strategy that I call clearing the fractions. And it operates on the same principle here, but it's less clumsy. It's more efficient. And now we can simplify. This, of course, is going to give us negative h. And again, cancels, giving us -1. And I get to -1/4 in 1, 2, 3 steps instead of 1, 2, 3, 4, 5, 6 steps. So I highly endorse clearing the fractions as a less error-prone and more efficient way to go. Does that make sense to everybody? Has anybody ever showed you that? No. I wish they did. Okay. Good. Let's talk at this time. And that's good. If you had questions about the homework, I'm sure you would have put them on the board.
Oh, that isn't what we're talking about today. You're just showing us.
I'm just showing you
okay.
an alternate way of doing it. Yeah. Algebraically, it's equivalent. Okay. So today we're going to talk about an alternate form for dy dx. Just to review from yesterday, dy dx represents what, first of all? The slope of the tangent line. That's exactly right. And the slope of the tangent line also represents the instantaneous rate of change. This is its short name, actually. The full name identifies the two variables of y with respect to x. And there will come a time in the future when we're going to need to be careful about the variables that we're talking about. How many of you guys go by a short name and you get called by your full name when you're in trouble? So that's a thing. And this guy's full name we're going to use not when we're in trouble so much, but when we're going to need to be clear about our variables. So this is the language that goes with this. And our form so far has been to take that difference quotient, which is the average rate of change, and we're going to make that average rate of change into an instantaneous one by using a limit. And that's our story so far. Now we're going to come back and we're going to do exactly the same thing. We're going to take an average rate of change and we're going to convert it into an instantaneous with a limit. But we're going to accomplish that with a different labeling of our points. Remember yesterday that we took a function f and we took a point c and a point x, and I asked you to come up with the average rate of change over the interval of c to x. And do that again to refresh your memory. What's the average rate of change of my function f on the interval c to x? Go. Write it. Find the average rate of change of f on the interval c to x. And you can label it either as average rate, or you can label it as delta y over delta x, and that should be equal to f of x minus f of c over x minus c. Change in y divided by change in x, and it's all in the label. And now what we're going to do is to take this average rate and we're going to turn it into an instantaneous rate, giving us the slope of the tangent line at the point C. So this is a secant line cutting through the curve. Its slope is going to be delta y over delta x. And now I'm going to use a limiting process to bring the point x in towards the point C so that we get a tangent line, and the slope is going to be equal to dy dx evaluated at x equals c. And so to do that, I need to actually bring this point in towards c. So what limit should I take? That's it. That's exactly it. So if this is my average rate here, then the dy dx at x equals c is going to be found by the limit as x goes to c, f of x minus f of c over x minus c. And we call this the alternate form for dy dx. Why do you think mathematicians who like efficient stuff would have two forms instead of one? Contemplate what you're learning for just a moment. Why would you want to have two different ways to compute the same thing?
For certain situations.
For certain situations, what?
One would be easier than the other.
Yeah, that's it. For certain situations, one is going to be easier than the other. And so we want to have the form, limit as h goes to 0, and the alternate form, limit as x goes to c, as tools in our back pocket so we can pull out one or the other as is appropriate. Phillips screwdriver, Whitehead screwdriver. All right, so there's our alternate form. Now, let's actually see how this might get used. Suppose I've got f of x equals x squared, and what I'd like to compute is find dy dx at the point x is equal to 2. And so now I'm going to do that by appealing to the alternate form. Actually, I'm going to write it literally like this. I'm going to start off by writing my form exactly as it is. Yes, every single problem, because it keeps the two forms clear in your mind, and you really need to keep them clear in your mind. Now I'm going to go ahead and fill in numbers. Now f of x is going to be x squared. And f of 2 is going to be 2 squared, which is 4, all over x minus 2. Huh, what do you see?
We canceled.
Yeah, we see some cancellation. But this time, instead of canceling by expanding a square, I'm going to end up canceling by factoring. So this form is more useful when factorization gives me something convenient. Tell me how this is going to go. Brian, tell me how this is going to go.
X plus 2, x minus 2,
Okay.
x minus 2, x plus 2.
No? What are you missing?
Limit to x goes to
Yes, that's right. This is not an optional decorator. I would not waste time writing something unnecessary. Ever. I'm far too impatient. Far too impatient to want to waste time writing something that is not necessary. So if you are skipping some stuff that is in the form, you're doing it wrong. And what you are about to do, Brian, is you are about to tell me a false thing. This does not equal this. This is a polynomial function, and this is the limit as x goes to 2 of that polynomial or rational function, really, as you have it written. You see the difference? Now that's the same. Keep going, Brian.
So x plus 2,
You didn't learn your lesson.
limit x goes
Say that first. Write that first. Okay. What does that equal?
to
4. Notice no limit here, because the limit as x goes to 2 of x plus 2 is, according to our polynomial theorem, 2 plus 2. Yes.
I don't get how you got like from the first step to the second step.
Here?
Yeah, did you plug in secret 2?
What is f of x?
X squared.
And what is c?
C is equal to x.
C is the value that you're evaluating at right here.
Oh.
And
Then
so
why can't we just write like limit x equal to 2 in the first place?
we do. because we're writing the form to remind ourselves of what the form is,
So,
because I'm the mom.
so why do you have x squared over, no, wait. So, the second step, why do x squared minus 4 is equal to 4 minus 4, which is plugging, never mind, I can get it down.
So, good. So, I'm glad you asked that question. He's confused about the difference between the c and the x. The c here is going to be our fixed point. It is the point of tangency.
So basically we skip a step by saying f of x minus f of 2.
Yes, that's right.
Okay.
Yep, that's exactly it. And just to go back here so that we're clear on this, what's happening is that I have a fixed point c that is not going to change. That's where I'm drawing my tangent line. And I'm now going to let x in my expression here go to c so that the denominator shrinks to 0. The thing that both of our forms have in common to help you distinguish them is we always have the difference quotient, delta y over delta x. And then we let the denominator of that quotient go to 0 for both forms. So let the denominator go to 0 here, I have to let x minus c go to 0, which means x is going to c. That's the purpose of having x go to c, it's so that I shrink the width of that interval down to 0. Questions, comments, or jokes? I have just barely enough time, maybe, so we're going to try another one. Construct the line tangent to f of x equals square root of x at x equals 9. And because I'm looking for a tangent line, therefore I'm going to need a slope. I'm going to need a point. You know what? Before I do this, I need to talk about Euler notation. Remember the fight between Newton and Leibniz? Leibniz writes his derivatives like this, dy dx. Excuse me, he writes his tangent line slopes like this, dy dx. Newton writes them in a slightly different way. That way doesn't get picked up, but Euler and Lagrange, mathematicians coming after him, have their own notation that I want to share with you, and that notation is going to be f prime of c. In the book, it looks like this. It's just an apostrophe. So you can write it like that if you want to. I use a downward pointing triangle. Notice it's downward, not upward pointing triangle, to indicate the prime sign. And this is exactly equal to dy dx evaluated at x equals c. These are synonyms for each other. You're going to see that both of those pieces of notation. Exactly, that's why I use the triangle. In the book, it's a little more clear because the prime sign slants a little bit. You'll see it when you read the book. So coming back up here, if I were to use the Euler notation, then I would say that my slope is going to be the dy dx, or the f prime, evaluated at x equals 9. And I'm going to say that my point is going to be 9 comma f of 9. In other words, on my curve here, y equals square root of x, I'm going out to x equals 9, and I've got a point 9 comma f of 9, and I'm going to slap a line on this, and the slope of that line is going to be f prime of 9. And that uniquely determines the line that I draw. I go to this point, I tilt myself to the right slope, and go. Can everybody see that picture in your mind? So, now it's just a matter of computing. Point 9 comma f of 9 is easy enough, 9 comma 3. And now I'm going to use the alternate form to get my slope. Why did I choose the alternate form instead of the form we learned yesterday? Well, it's about 50-50. This is a situation where either one could have been used. And I'll write my form first. F prime of c equals the limit as x goes to c of f of x minus f of c over x minus c. And now I'll go substituting. My c is 9. The f of x is square root of x. Oop. C is 9. And so f of 9 is the square root of 9. And there's my set. What do you think about this limit? How should I evaluate it?
Can you count divided by square root of x plus 3?
That's it. We're going to rationalize. And when we rationalize, root x times root x is x. Negative 3 times 3 is 9. And there is my common factor that can be canceled. Cancel, cancel 1. And now as I let x go to 9, then I get 1 over 3 plus 3, which is 1 over 6. And there's my slope. So having gotten that slope, I now go put it back into my work over here, 1/6. And that gives me enough information for my line. What's the equation for my line? Everybody should be able to do it from this information. What's the equation? Before you get there. Y. You can do y equals, but it's easier to use point slope form.
Oh, yeah.
Y
Minus
3
equals
1 over 6 times minus 9. It's a little slow on that one.